Okay, this is the second and final of the sort of background workings videos, just telling you a little bit about how NTC calculates travel. So I said before that from each zone there's a set of all other zones that you can get to, and that's basically every zone in the city. But I'm just going to consider 2 here. And you can actually get to those zones usually by a number of different modes. So let's say you can get to B by walking. You can get there by public transport. You can get there by car. And remember, B has an intrinsic value, right? So the value of visiting B, and that's based on the number of activities at B. So let's say B has, I think we said before, it had a value of $7.50. And we worked out before that the cost of getting there by car, I think it was, I can't remember, let's say it's $5. Let's say the cost of getting there by public transport is, so it takes a bit longer, so it's mostly a time cost, and maybe you have to do some waiting and stuff and you don't like that. So the generalised cost by public transports, let's say that's $8, and it's a long way to walk. So there's no money cost involved with walking, but there's a lot of time cost, so let's say it's $20 to walk to B. So as you can see, there's 3 different ways of getting to B. There's a generalised cost, a value of B. And so for each mode, we can work out the net value of B. But let's not do that just yet. Let's just think about if we were going to go to B. So conditional that we actually were going to go to B, what would the mode split be? And that's just going to be a simple, again, a multinomial legit on the mode choices. So the probability that we walk is going to be, it's going to be e to the power of minus 12.5. And that minus 12.5 is basically the $7.50 value of getting to B minus the $20 cost. So $7.50 minus 20 gives us minus 12.5. So, and then it's the denominator, just to make sure they all sum to the probability across all the modes sum to 1. It's e to the minus 0.5 plus e to the 0. So that will be the probability of walking, and let's say that's going to be approximately 0. So if you actually do that, nobody walks, and let's say, again, I haven't done the actual calculation, but just for argument's sake, let's say 90% of people go by car and 10% by public transport, based on the relative costs of the 3 modes. So you can see that based on the intrinsic value of the destination and the relative cost of the different modes, we come up with a net value by each of the modes, and we can use that to get the mode split, basically using a simple equation. And so that's basically it. So from that, you can work out by any mode you like. I've only shown 3 here, but clearly this is generalizes to however many modes you like. But by whatever mode you like, from any destination to any destination, by any mode you can calculate the mode split between any pair, and you can calculate the net value of any destination by any mode. So that basically gives us everything we need to calculate travel demand, because we can work out, let's say, how attractive this destination is, taking into account its intrinsic value and all the costs of getting there by all the different modes. And we can do that for the same for C, by all the modes for getting to C, and that will tell us the mode split between each pair, and also how many more trips there will be between A and B than between A and C. So if it's really costly to get to C, you have to drive a long way to get there by car, and so the car generalised cost is not $5, but let's say it's $50 to get to C, then you're going to have many fewer trips to C than you are to B. And so hopefully that's clear from the previous video on the underpinnings and this one on the mode split, basically how we calculate the destination, choose the destinations, and how we choose the modes. So with all that, after we do all that, for each A, we have we know of all the trips from A, let's say 50% go to B, 20% go to C, 30% go to E. Now, of course, the city we have has many thousands of zones, so really, in fact, you got a whole bunch of these possible destinations, and the probabilities involved are really small, so it might be a 0.01 chance of each one, but just to forget about all that and keep it conceptually simple, if there are only 3 other possible destinations, so if our city comprised of just 4 zones, and we know that the number of trips from A is just dependent on the number of activities at A, all we need to do is work out the mode split, the mode split between all the destinations. So we know the number of trips from A, and we say, okay, half of them go to B based on the cost of getting to B and the value of B. 20% of them go to C based on the cost of getting to C and the value of C. 30% of them go to E based on the cost of, based on the value of E as a destination and the cost of getting to E. And that's it basically. The only really point to note here is that there is a slight wrinkle that I've glossed over, and that is that it's the number of trips to and from each destination is fixed. So, and I said before that's proportional to the number of activities. So if A has, we know up front before doing any calculation about relative costs or whatever, let's say that A has 10,000 trips from it, going from it, and also 10,000 trips coming into it. They always have to be the same, just for symmetry. 10,000 trips coming in, 10,000 trips going out. So if we know there's 10,000 trips going out, then we can say, okay, well, there's 5,000 going to B, there's 2,000 that goes to C, and 3,000 that goes to E, and that's easy. And then we repeat that calculation for B and for C, and I don't know why I skipped D, but I did, and for E. But when we do repeat that calculation for B, C, E, and add it all up, we actually will find out that not necessarily will 10,000 trips be coming back to A. So basically our initial constraint where we said this should happen, there should be 10,000 trips from A and 10,000 trips to A, and the same for B. Right at the start, before we do any calculations, we will have a number where we know there should be, say, if B has half the activities of A, then B should have 5,000 trips going to it and 5,000 trips going from it. And there's no guarantee that all those constraints are satisfied up front. So after you do your calculations based on the relative values of the destinations and the relative costs of getting there, you have to iterate around a few times just to make sure that all the constraints hold in terms of the number of trips to and from. So that's the only wrinkle that, and that's part of the reason why the software takes a little while to run. But that's not so important. That's just ensuring a constraint is satisfied. The really important thing to note is that everything's governed by generalized costs in the software. So except for, of course, the number of trips. So that's our constraint. The number of trips to and from A is fixed, but destination and mode choice is all governed by generalized cost provided that constraint is satisfied. Okay, so that's the end of the second video, just on the background about how the software works. We might go back and look at some of the results now.